Welcome, guys. And today we are going to see that how to find out the boundary layer thickness uh, for a flow, which is a case of fluid flowing over a flat plate. This is the same thing what you have learned in fluid mechanics. The same kind of problem we are going to learn in heat and mass transfer when you are talking about when you are learning about convective heat transfer. Okay, so I have taken this problem from one of the good fluid mechanics book, and it says that air is flowing at 30 degrees Celsius and over a flat plate, and it is having a free stream velocity of 5 meters per second. We want to find out the boundary layer thickness at a distance of 0.2 meter, zero point 0.5 meter, and zero point 0.8 meter, and values are given here. Different values are given here for calculation purpose, and the values what they have calculated is like del is equals to 4 mm at zero point 0.2 and zero point 0.5 it is 6.325, and at zero point 0.8 meter it is 8 mm approximately. Now what we are going to do is we are going to find out this thing. Right now in this example I am not concentrating on a CFX and a CFL, coefficient of local and average skin friction coefficient. So I request you to uh, see the next video in which I am going to calculate these values also. Okay, so right now what I'm going to do is I'm going to click workbench, and then it is going to be open. And when I'm going to click on CFX, it will this new module will going to open. And I'm going to double click the geometry because I have to create a geometry. So this was opened here. Now first of all I have to select the unit. So I have selected millimeter. Now I have to select the plane. So I have selected plane, that is YZ plane, because I want to have the flow in X direction. Then I will going to look over this particular plane, and then I'm going to draw a rectangle. This rectangle, why I'm drawing a rectangle here, because I have to replicate a control volume over the flat plate. So that means when I am talking about a flat plate, just have to take care about the top surface of the flat plate, and when I'm doing that I have to create a control volume, and you may say imaginary control volume, which is over the flat plate where the fluid flow is going on, and it's a free stream condition, so it's a type of an atmospheric boundary condition, right? So that is what we are doing here. So for that I am going to just going to create a volume which will going to have a certain thickness, like I am giving here 500 mm thickness width of this particular cube. And then again I am going to select the center part so that I could give the height, vertical height. I am giving it as 150 mm, and then I am taking the horizontal distance, and then I'm going to define it so that it could be symmetric. So 500 means half of it is 250. This is the box I have created. Now I am going to extrude it in next direction. So when I'm going to extrude it in the next direction, I'm going to take like I want 1000 mm as a length of this particular volume. So I'm going to generate it, and so finally I got a simple control volume of certain dimensions. Okay, now I can solve this problem with CFX, sorry, Fluent also, and that Fluent problem can be done more accurately if I'm going to take a two-dimensional fluid flow, uh, you may say, problem. But I would like to solve the same thing in CFX, and want to know that how exactly it is behaving when I'm taking a three-dimensional flow. So how much closer the values are. So that is what I want to check. So meshing was getting opened. Now the most important thing what we are going to learn in this meshing part is that we are going to introduce inflation layers. If you want to capture the boundary layer, inflation layers are very much necessary on the plate. Okay, so let's see that this is the diagram. Okay, so this is the model. On this model, I will going to give the names of all the surfaces first of all. So I'm going to give this name as base plate on which the flow is happening. This is the base plate. Now, as per the direction, this is the inlet, and this face, and this face are the atmospheric openings. So I am going to name it as atmospheric openings. And then accordingly, this face should be the outlet. So I am going to give it name as outlet. Okay. So it is not necessary to give the names in capital letter. It can be smaller also. So I have created four faces here. So you can see inlet, base plate at the bottom, opening at the top, and outlet here. Okay. So now just when I'm going to click on the mesh, I have taken the solver preference as CFX, and it is equals to relevance equals to 100%. Then the type of relevance center, I want it as fine. Okay, now I'm going to do the meshing straightforwardly. Before that, I'm going to select the method. Here the body will going to be selected, and then I'm going to select the method. Here automatically I'm selecting the method and I'm generating the mesh. So if you're going to see this, the mesh you are going to see is good coarse mesh. Although we have taken it as fine, but still it's a coarse mesh. Okay. Now I want to introduce inflation here. Why I want to introduce inflation here? Because I want to capture this boundary layer, right? So for doing that, I'm going to click on mesh, insert inflation. Then I'm going to select the body in which I want to create the inflation. So I'm going to select geometry. Then I will going to create select the boundary face on which I want to create the inflation layer. So this is apply, and then I'm going to generate the mesh again. So now when I'm going to generate the mesh again, so automatically initially it has taken quad elements. Now see let whether it will going to take the quad element or it will going to take the tri element. So they have taken tri elements if you are talking about inflation layer. So it is not suitable, or you may say compatible. If I are going to use a face mesh, it is not possible to have an inflation in that separately. So because quad elements are ultimately a cuboid or a cube, so they can be used as an inflation layer. For that, you have to do edge sizing, and face sizing accordingly. Right now, I have taken this, and you can see that inflation layer is seen on the boundary. So here you are going to capture the parabolic nature of the flow. Now, if you can see that if it is 150 mm, the total edge length is 150 mm, the size of inflation layer is very high. It is very much high. So I should reduce that. So by seeing the problem here, the at point 0.8 meter from the leading edge, the boundary thickness is coming about 8 mm. So it will be better that I could restrict this inflation layer well below 10 mm. So I am going to tweak this inflation part, and I am going to select a number of layers I want. So if you are going to see here how many layers we are having, 1, 2, 3, 4, 5, 5 layers are there. So I am going to take it as 10 layers. I want to have more precise kind of layer here, and then I am going to use the inflation option, and in that I am going to define the total thickness. So total thickness is equals to how much I will going to take it as, let it be, I will going to take it as 10 mm only. So now I am going to generate the mesh again, and after generating the the mesh will going to look like this. Yes, and finally I got a mesh here. See, previously it was very bigger. Okay, now it is only distributed 10 mm away from the bottom face, and see, you can see that how exactly it is behaving here. So this is how it is going to capture the inflation part, that is, sorry, boundary layer profile. So right, this is how we are going to do the meshing. Meshing is complete. No need to do anything else right now for this condition. And now I am going to shut it up. Now I am going to set up the. I am going to update this part, and setup will going to be refreshed. It will going to have that green arrow type icon. Okay, and yes. Now I am going to click the setup, and when I am going to click the setup, this will going to open. Yes. So this is the meshed volume I am having, and now the first thing I have to define whether the flow is steady or transient. I am taking it as steady. Okay, no problem. Next thing I will going to define the basic values. That is the type of material. I am taking air at 25 degrees Celsius. if I want to have air at 30 degrees Celsius, I have to create a new material. So instead of that, the better thing is I am going to take this air at 25 only, and then the reference pressure is 1 atmospheric pressure. The fluid model will be in heat transfer is not there, so I'm going to take it as none. I can even take isothermal if it doesn't make any difference. Now in turbulence, I am going to take laminar. The reason behind is in the problem itself, you can see that the flow is laminar because the value is 1.5625 into 10 to the power of 5, which is less than 5 into 10 to the power of 5, which is the limit for atmospheric boundary layer Reynolds number. Okay, so if you want to identify whether the atmospheric or open channel flow, whether it is laminar or whether it's turbulent. In that case, for atmospheric boundary layer flow, the limit is 5 into 10 to the power of 5. The same way you are having limit of 2000 or 2000 to 4000 for this pipe flow, or you may say conduit flow. Okay. Now, after doing this, I'm going to define the flow as laminar. Then I'm going to click OK, and then I'm going to define the boundary condition. The first boundary is the inlet. I'm going to name it as inlet velocity VL. Okay, then I'm going to select the location. The location is inlet. In that boundary, I'm going to define the velocity, that is 5 meters per second. Then I'm going to click OK. Now you can see here at the inlet, it is having arrow which is in the direction of flow x direction. Now I'm going to take the next thing, which is the wall. I'm going to call it as base or plate. I'm going to name it as flat plate. Okay, I'm going to call it as flat plate. Then it is a kind of a wall. So I'm going to select boundary type as a wall, and in that wall I'm going to select the base plate as a location. See, you can see here I have selected this one, and now the kind of boundary condition, moment, mass and momentum is no slip boundary condition. So I'm going to apply it, then I'm going to click OK. Then next will be to define the openings, that is these three walls which are there, open to atmos. So open to atmos means it is actually nothing but an imaginary wall which is directly in contact with atmosphere, and it will not at all going to act as a wall. It will just going to act as an open atmosphere. Okay, so now I am going to take it as opening. The boundary type should be opening for this kind of cases now, and I am going to click the opening as a location, so you can see here. So after doing that, what will going to happen, I have to define what is the condition of atmosphere or the environment near it. So in the opening pressure and direction, I am going to take it as static pressure. So because it is open atmospheric pressure, so I am going to take it as 0. And when I am going to apply here, you can see that this is resembling a case where fluid is easily accessible in both direction. It is bidirectional arrows here. Okay, that means fluid can enter here and fluid can get outside also from this control volume. Okay, why? Because it's open. That is why it is showing you like this. Then the next one is, and last one is outlet. I am going to define the outlet also, and outlet. Next outlet already it has taken. Now it will, instead of average static pressure, I am going to take static pressure here 0, because reference pressure is already 1 atmospheric pressure. So I have defined all the boundary conditions here. Now the next step is to define the convergence criteria. So, and the number of iterations. Here I am taking maximum 1000, and then after that, if I am going to click the convergence criteria equals to 1 to the power of -4. This is so, but I am going to take 0.01. Okay, 0.001, that is 1 e to the power of -3. Okay, itna le liya. Now what I'm going to do is I am going to run the analysis. All I have done, every setup has been done. Nothing has to be done more. Okay, now I'm closing this. Now instead of clicking the solution part and clicking on start run, I am going to just go right click on this, and then I'm going to click update. So update means start run. Okay, so update means start run, nothing else. Now, after doing that, if you want to see the solution monitor, when it will going to start, now you are going to have progress of the solution on this particular bar, hide progress, show progress. You can see if there is some error. You are going to have error also. You can show the message what kind of error. No, not connected to PS 627. It's an error which is not related to this. So now, if I am going to right click on this, I can see the display monitors. I can see this display monitor. I'm going to click that. So I'm going to have this solution. Okay, guys, I'm going to have this solutions here. On the left hand side, you are having residual graph, and on the right hand side, you are having iteration values. So how U momentum, V momentum, W momentum, that is momentum equation and continuity equation is going on. right? How I'm doing that, that is what has been solved here, going on, and it is giving you some values. So just for your sake, if you want to understand that, here you can see that the orthogonal quality is under the limit, and iteration has been done. I have done, click OK, and aspect ratio is again under the limit, so this is okay as per its calculation. So if it is saying okay, there is no error in your system, but if it is not, then it will going to show you some kind of error, and it will going to create an exclamatory mark here. So okay, analysis has been done, mesh is okay, results are, if you want to see the output at the end, you can see the velocities, density values, velocity values, pressure values here. Okay, some values are printed here. Even Reynolds number, if you want to see Reynolds number also, see, you can see here Reynolds number is approximately the same which has been calculated in the problem. Okay, 1.5625, it is 1.167 e to the power of 5. So both are same. Reason behind is that is that it's a perfect system, you may say. It is totally resembling the true nature of the system by using the formulation. And here we are using iteration method, and we are having a mesh quality. So definitely it will going to have little bit difference. Okay, still the Reynolds number, if it is 1.167 e to the power of 5, it is still under the limit. That is, it is a laminar flow. There is no a problem in that. So the Reynolds number is so like that it is defining. Then I am clicking outside. Okay. Uh, and I'm closing this. Now I have to click the result. So instead of clicking this result, I have already done this whole part, and now I'm seeing that values. Okay, I'm clicking this thing, this result, which is already solved in it. I have to create the analysis and everything. I have to create the line, and I have to post process everything. So that's why I'm not doing that here. So this is the part. Okay, I have drawn, see, this is a center plane, and at the center plane I have taken three lines at 0.2 meter, at 0.5 meter, and 0.8 meter. How to create a line? Just go in location, go to line, then give the coordinates here. Like if I want to have a line at 1 meter, and then in y direction it should be have the maximum value, and x direction should be 0, and then I am going to have approximately 100 points. I am going to apply it, and if I'm going to apply it, this is the thing, this is the length of the, this is the location of a new line. So I'm not doing that, I'm not using that. Okay, I'm removing it. Now when I'm going to see the velocity chart, how to add that, I'm going to select a new series from here, like this. I'm just showing you that. I'm going to show you that. Click, then line 1, then select x-axis, you are going to select velocity. On y-axis, you are going to select the y direction, and you are going to click apply. Now after that, you are going for data series again. You are going to use the second line, that is at 0.5 meters. You are going to select the second line, then you are going to apply. So you are going to have the second graph. Then you are going to click the third line, you are going to create another series, and then you are going to select the third line, and then again apply for the same variables. You are going to have these three lines. Okay, so finally you are having three graphs at three different sections. And then I have, if you want to identify what is the value of boundary layer, okay, then what you have to do is you have to export it. I am going to export it and going to write this in XY value. I am going to name it as XY value, and it is default, by default, CSV file. So I am going to save it. Okay, cancel. Nothing else. I have to do. I don't have to do anything else here. Now, second thing I want to show you that what exactly happening here is that you can see that in this diagram, initially there is no boundary layer which is having very small thickness nearer to the leading edge. From here we are having the free stream velocity. Slowly when we are moving outside, means we are moving away from the leading edge, the thickness of the boundary layer is increasing. That is what you have learned in your fluid mechanics part. Okay, so these are the locations. You can see that how exactly it is happening. Slowly the thickness, slowly the thickness is increasing, and that is what we are expecting, and it is showing you the same behavior, right? Now what the other thing you have to do is, if you want to verify whether the values what we have calculated and whether the values in this problem are same, or at least they are nearer to each other, then you have to check it. So I have exported these three values in CSV, three graphs curve values in CSV. Now what I am doing is I'm opening that file. So I have already opened that. Okay, I have already opened that, and you know one thing that in case of in case in case what is happening. Uh, okay, so what we have to take care is that this profile on a on a simple plate, this profile which is drawn, the point at which you are achieving the maximum velocity, that is free stream velocity, okay, is known as viscous region. This region is the viscous region. Okay, now at this point we what we generally used to say is that if the point at which the velocity reaches the point at which the velocity reaches 0.99 times of u maximum, or you may say free stream velocity. Okay, u maximum or free stream velocity, up to that point you are having the thickness of boundary layer. So this is the boundary layer thickness we are assuming here accordingly, what we know here at this point we are having. So this is the boundary layer del. So this is del. Okay, right. So as per this, we are having formulation here. You know this formula, how to calculate all this. So now just we are going to see that what are the values. Now in this graph, sorry, in this chart, I know what is the value of inlet velocity, that is 5, that is 5 into 0.99. So what is the value? 4.95. So in this chart I am not having 4.95, I am having 4.93, and then after the next value is 5.13, right? So what should I do? I should interpolate, but I am not assuming that, I am not taking that, I am just using the last value which is nearer to the maximum value I am having. Okay, so like this here I am having 3.03. So this is the location at 0.2 meters. The next location is the where we are having 4.95. Okay, if you are going to interpolate, definitely you are going to get nearer values. So if you are having 4.93, you are having velocity 4.93 at approximately 3 mm. This is 3.03 mm, right? I have multiplied. What is the formula I have used? I have just multiplied it with 1000, so it is giving you the value of mm. In the same way, 4.90 is coming at 4.55 mm. This is 4.55 mm. In the same way, in the third chart, at the location of series number 3, that is at 0.8 mm, the value I am getting is 4.95 exactly I am having here. Say, by chance I am getting 4.95 here. And when I am doing that, the value of this boundary layer where I am getting 0.99 times of maximum velocity, that is 5, that is 7.58 mm. Okay. So the last value here in the question and here in this CFD solution, we are having very close values. So if I want to find out the value of error, okay, if I want to find the value of error, I would say, I would say it will be very much lesser, I think, I feel. So I just am calculating that. So it is, see, it is approximately 6%. So it is approximately 6%, right? So I'm just converting it to percentage. Yes. So it's 5.88% is the error between the last result at 0.8 meter distance and here. Now you would say that, sir, it's air is at actually 30 degrees, but you have taken air at 25 degrees. Definitely the density difference due to that 5 degree will have a drastic effect, and you are seeing that because initial values, or you may say the boundary velocity, boundary layer thickness values, which are we are assuming here, are still having larger error. It is a near about error, I think, as per the values shown here, the values are near about 11 to 12%, which is more than 10%. Okay. So as I already told you that 10% error and under 10% you can assume that your analysis is okay. That is happening here, right? For the at least for the last point, that is 0.8 mm. So guys, this is how you are going to perform analysis for boundary layer flows. Okay, whenever you are solving the problems of, sorry, Whenever you are solving the problems of flow over aerofoil, flow over a body, aerodynamic kind of flows, okay, projectile flows, everywhere, you have to go for an inflation layer. You have to calculate the boundary layer thickness. Okay, this is how you are going to. There is no such way to find out the value of boundary layer thickness in the software. You have to analyze the points by exporting it into this particular thing, that is Excel file, and then you have to see that. Okay, so I think it will definitely going to help you to understand how a boundary layer is developing over a surface. Okay, and you guys kindly practice on this. Create a different conditions, take a different kind of fluid, take a different kind of surface, and you may move on, and you can understand that how exactly this boundary layer is behaving. You can go for turbulent then, and how turbulency is giving you in values, how turbulency is giving you the flow profile. So this is how it will going to help you. Thank you guys. If you have any doubt, you may write on the chat.